Hello, my name is Rebecca Matasovsky. I'm an Associate Editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Cambridge Air Solutions. The subject is Path to Net Zero Energy using HCHB technology. Today's speaker is Dave Binz. Dave is the Director of Engineering for Cambridge Air Solutions. He holds a Bachelor of Science in Chemical Engineering from the University of Notre Dame and an MBA from Washington University. He has extensive experience in the high-efficiency heating, ventilation, and air conditioning market. He began his career with Carrier Corporation, serving the large commercial and industrial market with engineered solutions. He joined Cambridge Air Solutions as a regional sales manager and now travels North America speaking to engineers, building owners, and contractors on next-generation heating, ventilation, and evaporative cooling solutions. Dave, the microphone is all yours.
Thank you very much for that introduction, Rebecca, and thank you again for all of our attendees for being with us here today. And hopefully in this session we'll get a chance to learn about a exciting technology that some may be familiar with, some may have not been, if they have not been in the large warehouse industrial spaces, but ultimately provides a lot of value and some unique solutions to our end user engine engineering clients. So again, thank you by the way of the introduction, Rebecca. Again, my name is Dave Binz, and looking forward to spending the next hour here with you together. To get us started on the presentation, I wanted to talk about two key trends that we're seeing in our HVAC industry that has been prevalent for the last few years and really has become even more the forefront of our conversations. And that first trend is a massive increase in the need and the conversation around ventilation. It has been a long-standing tradition for ASHRAE to help improve indoor air quality in our buildings through the development of ASHRAE 6.2.1, even through as our high-performing buildings, we moved into LEED construction in 189. There's always been a continued strive for better ventilation, and this has been nowhere near as I would say forefront as it has been the last 2 years with the current challenge of the pandemic, and it has become a primary driver for many end users and engineers, the need for quality and high-performing ventilation systems. The second trend that has been ongoing for many years and has continued as we look in the future of the built environment is the focus on energy. How can we not only improve the built environment, indoor air quality, but also lower the energy footprints? I'm sure as we all know that the commercial building space utilizes quite a bit of our world's energy usage, and we spend a lot of time inside commercial spaces, and we must continue to drive energy efficiency and lower energy usage in all of our commercial spaces. And so you think about those two key concepts, increased ventilation and lower energy usage. Typically, those two themes have somewhat of a tension or in conflict. How can I increase my ventilation while lowering my energy usage? Typically, end user engineers are challenged with that trade-off in order to make the buildings safer, in order to have better indoor air quality with more ventilation rates. Typically, I'm going to have some kind of energy penalty for increasing those ventilation rates. What I want to talk about today is technology that is deployed in spaces where we have been able to increase ventilation rates and lower the energy footprints, primarily in these large warehouse and fulfillment center spaces. So again, like I said, for those on the call, we are here to talk about a technology called HCHB, or high temperature heating and ventilation units. For those that have not been in the large warehouse, distribution, or industrial space, this may be a new technology for you. But what is HCHB? Well, HCHB, as defined by the industry, is a 100% outside air direct fired heater with a performance criteria of greater than 140 degree temp rise and greater than 150 degree discharge temperature. So those key temporized discharge temperature is what makes the high temperature heating perspective. And then we qualify the ventilation units in such that this system has fully modulation temperature controls to meet both our ventilation and our space heating requirements. So this, in a nutshell, is the performance criteria for HCHB, and we'll talk in depth about how that impacts the sizing, the deployments, and ultimately the energy efficiency of heating high bay manufacturing, warehouse, and fulfillment centers. So again, for a little bit of a history lesson, this technology and the concept of heating buildings with outside air is not new. It has been around for some time. Really stems back to the mid-90s, where Cambridge introduced the blow-through high-temperature heat ventilation system for really design, build, new construction mechanical contractors. And what they saw is they saw these large open spaces were primarily being heated, and still to this day, with unit heaters or smaller terminal heating systems really strung along the perimeter of a building with large gas connections, many pieces of equipment, many electrical connections, and really no ventilation systems. And what early adopters saw is that they could lower their install costs by over 40% by utilizing larger systems, by utilizing larger zones, and ultimately greatly reducing the number of installed units from anywhere from maybe 30 to 40 systems down to 6 to 8. Additionally, end users saw their energy bills cut in half. The benefits of the high temperature heat and ventilation systems and pressurization saw that not only were they paying less upfront for their HVAC systems, but ultimately the operating cost of these buildings was greatly reduced over time. And thirdly, these buildings primarily had no mechanical ventilation before. They primarily met ventilation criteria with I would say, a loose and lax requirements of just having a general leaky construction or many operable doors such that they would meet a minimum ventilation criteria. However, what this technology did is actually introduced forced mechanical ventilation where these buildings did not have. And when you look at those three key concepts, lowering your install costs, lowering your energy bills, and improving the indoor air quality by providing free ventilation is what transformed that warehouse market and continues to be adopted and deployed in many more industrial and fulfillment center applications today. So we're going to go through three key education statements today that I hope you have a chance to walk away from. And those three key pillars are the inherent safety of the technology, the energy efficiency of the technology, and ultimately the simplicity of design. How does this system provide multiple technologies in a single piece of equipment to provide more value to our end users and installing contractors? So again, from a familiarity perspective, for those that are not familiar with HCHB or maybe not be familiar with direct fire technology, is what is HCHB and what kinds of systems are we talking about? So many in the presentation today may be more familiar with the traditional makeup air or draw-through system, which is primarily deployed across either small kitchen systems or maybe some industrial ventilation systems, i.e. paint booths or process exhausts. But ultimately, this technology is a 100% outside air, direct fired combustion system, meaning direct fired, there's no heat exchanger, no flue losses, such that 92% of the thermal energy in the combustion process is delivered to the space, and it's actually 100% combustion efficient, such that there are no wasted energy from the combustion perspective. All of the available energy is delivered to the space. This technology we're talking about today, which is the HCHB, is similar in design of the draw-through makeup air with one key design difference, but a massive performance difference. What HCHB does, by moving the blower in front of the burner, where our mechanical devices are now in the cold air stream, we now can achieve that performance spec of HCHB by being able to dialing up the discharge temperature, dialing up the temporize, such that we can now achieve a 160-degree discharge in a small box. We can now achieve a higher temporize and a higher leaving air temperature without compromising any of our mechanical equipment, any of our belts, any of our bearings, or any of our motors. So it allows for a higher capacity in a smaller volume. And we'll go into more in depth in the energy efficiency side about why this is impactful from a low energy footprint. But first, let's talk about safety. How is it safe for either these makeup air equipment or the HCHB technology to deliver all the products of combustion into the space? And really, when we talk about safety with combustion equipment, the core concept for us to discuss is carbon monoxide. Carbon monoxide is one of the byproducts of incomplete combustion and can lead to unsafe conditions if not mitigated. So I'm going to talk about a report done by the CDC that actually looked at all the CO exposures in the U.S. And what they found is that every year there's about 15,000 emergency room visits and about 500 unintentional deaths in the United States each year caused by carbon monoxide poisoning. And inside that study, what they found is that about 2/3 of those CO exposures, the root cause, the cause of those was actually an automobile exhaust, such that automobiles were creating the CO exposures that led to an unsafe environment. About 1/3 of those situations were caused by a home heating system, actually an indirect fired combustion device. And inside that study, they were not able to find any single CO poisoning system, CO exposure, that was a cause of a direct fired combustion device, such that a system that is designed to deploy and deliver the product of combustion to space was actually not the cause of any of the CO exposures across the U.S., even though they are widely deployed in many commercial spaces. So I'll ask the question, why? I'll let you sit there and think, what is it that causes the CO levels inside these spaces to reach unsafe levels? What is the reason that even an indirect fired system, a mechanical system that is designed to separate the product of combustion from the delivered air, was actually the resulting in 1/3 of the CO exposures, yet 0 systems from the direct fired? And ultimately, if you ask yourself, which we many times do in our engineering principles, is ask us, what is the root cause? How do we get to the root cause of each of these problems? And what is the single root cause for each of these 500 deaths that the U.S. typically sees every year? And it's lack of adequate ventilation, right? Dilution is the solution to pollution. Loved learning that in some of my early years in the HVAC industry. Ventilation is the key safety device for any indoor air pollutants, whether that's CO or any other contaminants. And in most cases where we do have CO systems, detection systems, maybe before garages, when we see those CO levels reach an unsafe level and we have those sophisticated controls, the immediate next step is to increase our ventilation systems, to turn on our ventilation systems, to reduce those CO levels. And if we think back to what is the core performance of the technology we're talking about today, is that these systems are 100% outside air and they are designed to provide ventilation. There is no way that you can separate the ventilation component from the combustion component of these technologies, such that you will always be ventilating whenever you're combusting. You will always be bringing in fresh air whenever you are heating. And these products are certified to a very stringent safety standard, ANSI 3.4, to ensure that we have adequate ventilation and low product combustion to be able to keep those systems safe. Really, I like to use a term that is utilized in other parts of the world when we talk about engineering safety systems, which is inherent safer design. And really, that's at the core concept of the safety standard of the ANSI 3.4, is to make sure that we do not require engineering controls to make it safe, but actually the ventilation component of these devices make it inherently safe, such that we will always be ventilating and we can never create an indoor concentration above the discharge concentration of CO. For those, excuse me, for those that are unfamiliar, pardon me, for those that are unfamiliar with the safety standard, what it is, it certifies that all of these products and all of these systems are able to achieve less than 5 parts per million CO's added concentration. So in a worst case scenario, if we have a 7, 8, or 9 parts per million outdoor air CO, the highest that the system can ever provide is 5 plus that, so 5 plus 9, 14, and we can never reach any levels above our discharge. So we will always be ventilating and always lowering the CO levels inside the space. So that's our safety component of the presentation today. And now let's get into energy efficiency. Really, if you are new to ANSI ZA 3.4 or direct fired systems, new to HCHB, if your first thought wasn't how is it safe to deliver positive combustion to the space, your second thought might be how is it safe or how is it energy efficient to heat a building with outside air? Many of us are probably taught at a very young age to shut the door, you're letting the cold air in. We're going to be, often in concept that I've heard from many parents, and now as I prescribe to my kids, you know, we're not trying to heat the entire block. We're just trying to keep our house warm. So it's kind of in our DNA that we want to lower the outside air requirements in the building to keep it energy efficient. And as engineers, and in the ASHRAE world, we know that every building must have outside air. We can't completely eliminate outside air from all buildings, and that every building is designed for human occupancy must bring in outside air and fresh air. And that's what the ASHRAE 62.1 standard does, is it gives us a direction and a guideline for how much ventilation buildings need in order to meet safe indoor air standards. Secondly, those systems and these buildings must get this air either from natural infiltration or mechanical ventilation. Many codes across the country have come a long way in the last 5 years to making sure that actually we need mechanical ventilation, and very few, I would say, building standards allow us to use all natural infiltration to meet a outside air requirement. But ultimately, we know that all buildings need to breathe in order to allow fresh air for the occupants inside the space. And now from an energy efficiency perspective, if we look at these large warehouses and high bay spaces, this heating requirement to heat the air from outside conditions to space conditions is what we call the air load. And in these large buildings, this air load can be a massive percentage of the overall heat load in a large warehouse or fulfillment center. So let's talk about how is it and what is the most energy efficient way to heat the air load in these spaces. Well, let's take an example. Let's take a large warehouse that has a 10,000 CFM outdoor air requirement, and we have a 0 degree design temperature. In order to meet the air load requirements, I must heat that air from 0 degrees, 70 degrees, which is the internal design temperature for this building, and that equates to about an 869 MBH output. And if we are talking about energy efficiency, the most energy efficient way to heat this air is utilizing a direct fired makeup air system. With no heat exchanger, no flue losses, and a 92% thermal efficient system, I now have a very simple and a very energy efficient way to heat the air load in the space. Now that's only half the formula. What about the conductive loss? What about our skin loss? What about all of the energy loss from transmission we have by having cold air outside, warm air inside, and a cold thermal mass separating the air barrier? Well, one system or one method that is often deployed is we add some element of an indirect fired recirculation systems. We may either add additional unit heaters, some kind of indirect fired package rooftop, maybe an indirect fired air turnover system, or other kinds of indirect fired infrared systems such that require the recirculation of indoor air with an indirect fired system. However, what you'll know is that all of those systems are going to be limited from an energy efficiency perspective from the flue losses inside the heat exchanger. But what about this simple concept? What about the concept of turning up the discharge of your 100% outside air system and utilizing the 100% combustion efficient, no flue loss combustion process such that every degree of discharge temperature above space temperature becomes usable heat to counteract any conductive losses? We're talking about energy efficiency here, so this is some pretty simple math. Is 92% greater than 60 to 80? Absolutely. So we're going to try to use the highest energy efficiency combustion process available. And in essence, that is what takes our standard off-the-shelf kitchen ventilation makeup air system into a high-performing, low-energy HCHB system, such that by dialing up the discharge to the maximum safety standard allowable, we can then create more heat and more energy to counteract any skin losses without adding any ventilation air, without adding any recirculation air, and without adding any additional systems, such that now we have a fully functioning high-temperature heating and ventilation system. And what this simple principle allows us to do is that the HCHB system gives us an additional 90 degrees of temp rise, or 1.1 million BTUs of usable heat to heat any conductive losses. So as we said in our example before, our air load is only a small portion of the total heat loss in the building. And now with this single system, I can not only meet my ventilation needs, but also my space heating needs, and a fully modulating system to match the indoor space conditions. So also, let's understand which kinds of environment we are talking about today. We are typically talking about large distribution, warehouses, or fulfillment centers that typically have extremely high ceilings. In some cases, it is typically you're going to see 30, 35, maybe even 40 feet of finished of one space between floor and ceiling. And if we're talking about heating that large space, temperature stratification is going to be one of the energy hogs of these buildings. When we're trying to heat the floor where the buildings are, where our human occupants are, we want to make sure that heat is at the floor and not at the ceiling. And as air and heat wants to naturally rise, we must deal with this stratification somehow. So how does HCHB deal with stratification? Well, there's many ways to destratify a space. There's many additional technologies that you can add to a space, whether that's HVLS fans, pair fans, zoo fans, really even simple paddle fans to move the air around and try to push that warm air that's going to naturally want to rise to the ceiling and push it down to the occupied floor. But what some HCHB technologies typically deploy is what we call high velocity discharge, such that by inducing a large air turnover, by utilizing a high velocity discharge, we can induce a large air mixture, a large air distribution, and a large air turnover in the space without having to add additional fans, without having to add additional ductwork, without having to add additional volume of air being recirculated. So if we think back to that previous example of our 10,000 CFM, 2 million BTU HCHB system, by delivering that outside air at a high velocity, by utilizing Bernoulli's principle, I can induce and pull that warm, stagnant, stale air at the ceiling and drive that air down to the floor and induce a large volume of air. In essence, what HCHB will do is they take that 10,000 CFM high velocity air, and through a roughly 10-to-1 induction ratio, we can create a 100,000 CFM low velocity air mixture, such that we've seen in these large open spaces that they can get anywhere from 2 to 5 degrees of temperature variation from wall to wall, floor to ceiling. So massive coverage, massive heat distribution with a single device, with one fan, and with one ventilation device. Now, not every warehouse, not every distribution center is going to be the same. So we must think about how is the building being used, where are our operable doors, how are they utilizing the rack systems, how dense are they, how are they being, how is those racks or is the storage product laid out in reference to our heaters. So obviously we must take into consideration how the building is being used and how it's being set up in order to get good temperature distribution. But by utilizing some of the key design teams available to you, these systems can be deployed such to meet that 2 to 5 degrees temperature variation wall to wall, floor to ceiling, without adding additional air movement devices. Additionally, these systems can be mounted on the roof. They can be mounted through the wall. They can be mounted horizontally or vertically, and they are typically anywhere from 250 MBH up to 3,200 MVH. So even in a single device, these HCHB systems can operate up to 3.2 million BTUs of total heat capacity. And still, if we talk about how big these systems might be, 3 million BTUs of a system is really still all in with the entire ducted and distribution system is still less than about 2,000 pounds. So that single HCHB unit at 3 million BTUs can cover a pretty large space and not really take up a lot of footprint, not a lot of weight to distribute on the roof. So very flexible from a design perspective. So now I want to move into the energy efficiency side of it and talk a little bit more in detail about why high temperature and why blow-through becomes massively impactful from an energy efficiency perspective. So we're going to go into some granularity around the differences between HCHB and draw-through makeup air systems, particularly as it pertains to energy efficiency perspective. So again, let's familiarize ourselves. The system on the top, which is your draw-through makeup air system, widely deployed in kitchen ventilation systems, paint booths, or other process exhaust systems. And on the bottom is our high-temperature heating and ventilation blow-through system, where the blower is in the cold air stream. So let's talk about what are the differences. So we're going to be talking about, let's look at if I try to utilize a standard draw-through makeup air system and deploy against a standard HHB system, how is that going to impact my ability to heat a space? Well, both systems have typically a constant volume fan. The blower in the makeup air system is in the hot air stream such that it's processing less dense air. Less dense air. Density is not a concept that we talk about that much in our industry, but we'll go in more in detail later. And with the blow-through system, my blower is in the cold air stream such that it's processing more dense air. So when we are processing 0-degree air, lower density. And additionally, discharge temperature. Most makeup air systems, when I have the motor and the bearing and the belts in the hot air stream, they're typically limited in discharge temperature to around 120 degrees. Beyond 120 degrees, you might see belts, bearings, motors begin to fail at a higher rate. However, in the HCHB system, since my blower and motors and bearings are in the cold air stream, I can dial my discharge temperature up to 160, and those motors are happy as a clam. Lower mass flow rate and higher mass flow rate. We don't often talk about mass flow rate when we are looking at designing HVAC systems, but mass flow rate is really the core concept to this whole equation, which is the equation for convective heat transfer, which many on the call I might challenge we haven't seen since our intro to thermo days back in university. So this simple equation here is what governs our entire industry. And what it says is that the convective heat transfer, or the total heat transferred, is equal to the mass flow of air times the specific heat of air times the discharge temperature difference. Again, if you'll notice, that equation does not say volumetric flow. It says mass flow. Yet, how often in our daily operations, in our daily calls, in our daily designs, are we typically thinking about volumetric flow? And you may ask yourself, well, I use this simple equation every day, and it hasn't burned me yet. 1.08 times CFM times delta T. Well, there's one key assumption to that 1.08, which I'm sure many of you use, again, every day. And that key assumption is what we call standard air, right? 1.08 only works in one condition, 70 degrees and sea level. Now, I will argue that doesn't mean you have to go back in and reevaluate and redesign all of those mechanical systems you designed today, last week, or last year. But in most cases, in a lot of office spaces and recirculation systems, you're looking at it from 55 to 80 degrees. 1.8 might cover you. However, let's talk about our systems here. We're talking about the difference between 0 degrees and 120 degrees. Do we think there's going to be some element of different densities? Do we think that 1.08 standard correction factor will work? Well, let's look at it. And let's look at this convective heat transfer and see what the difference is in the ability to transfer heat by processing different densities of air. And if I take our draw-through makeup air system and compare it to a blow-through HHB system, the difference in density from 0 degrees to 120 degrees is about 26%. What does that mean from a convective heat transfer perspective? That means that by moving the blower to the cold airstream, HCHB systems can process 26% more mass per fan CFM. What that means from a convective heat transfer perspective is that I can deliver 26% more BTUs for every CFM processed. More heat, more energy, without more airflow. What about the other key variable in this equation? Discharge temperature. Both systems are constant volume. We're going to hold our CFM standard from a fan volumetric perspective. But how about discharge temperature? Because, again, our blower is in the cold airstream and we can process warmer and higher discharge air, I now have about 33% more convective heat transferred per CFM by having the ability to turn up the discharge temperature. That means 33% more BTUs transferred for every CFM processed by the constant volume fan. And now if I look at those two values, combine those together, this is where HCHB really starts to shine. By allowing for higher mass flow and greater discharge temperature, by combining that 26% and 33% factors, the HCHB technology on a per CFM basis can deliver 68% more energy, 68% more BTUs per CFM. So I can deliver more heat with less airflow. But really, when we talk about high-performing warehouses and fulfillment centers, we want to talk about how does this building allow for lower energy usage and how can we use less energy to heat our conductive loads. So let's go back to our conductive load equation we said earlier. How do we cover the conductive loads? Well, both the make-air system and the HCHB systems are going to heat the conductive load the same way. Whatever discharge temperature, whatever temperature I have above space temperature is really the only usable heat that I have to heat my conductive loads. They're both going to be 100% efficient. They're both going to have 92% thermal efficiency with no flue losses. But what about our ability to deliver net BTUs or usable BTUs to counteract any conductive loss? So now we're going to change the delta T variable slightly. We have our same discharge temperatures, 120 and 160. However, instead of comparing the full temperize, I really just want to look at the difference above space temperature. So think back to our previous example of 10,000 CFM, heat to 70 degrees. If I'm trying to counteract the skin loss, really it's only that usable heat above my space temperature that I can use to heat any of those skin losses. And in this case, the HCHB has 90 degrees of temperize above space temperature versus the 50 degrees of the draw-through systems. That's an 80% difference in net BTUs delivered per CFM. Massive difference. And if I combine those two key factors now, let's bring in back that higher mass flow rate with processing cold air, more dense air with the blower in the cold airstream, and now by having an additional 80% of net BTUs caused by the higher discharge temperature, adding my 26% and 80% factors, I now have 127% more net BTUs transferred for every CFM. If I hold my CFM constant, comparing these two systems, the HCHB can deliver 127% more ability to heat. That means smaller heating systems. That means less ventilation air requirements. That means ultimately less energy to heat the spaces. So I know that was a lot to go through. I know you probably weren't prepared to go through a convective heat transfer and dust off that whole equation today, but hopefully it maybe sparked some interest and some ideas about how the difference between standard air and actual air can affect our ability to heat, and really how it becomes a massive factor in deploying these types of systems. So thirdly, the last, I would say, key pillar that we want to talk about in designing HCHB systems is, again, the simplicity of design. And I alluded to this a little bit earlier in our presentation, but ultimately a single HCHB system can replace multiple typical systems that we deploy in these spaces, which mean greater value for the end user, and actually lower energy usage. So one 1600 MBH HCHB system also replaces the need for 6 high-efficiency unit heaters, some element of destratification device, and some element of a tempered ventilation system, such that one connection, one gas connection, one electrical connection, one blower can achieve my heating, my destratification, and my ventilation requirements. So as an engineer, I love simple, and I'm sure if you're a design engineer, you love simple. You love trying to utilize one schedule as opposed to many. So think about the beauty of the HCHB technology, is that it is one single piece of equipment, one electrical connection, and one penetration. This is actually a unique story that I had with a call with an architect down in Alabama that was designing one of these systems, and they had changed their design from many indirect fired systems with many flue penetrations to ultimately about 20% of the total connected uses and actually through wall. And so the architect was actually able to completely eliminate any roof penetrations so that he was able to improve the integrity of the building envelope. And as many of our architect clients can probably share horror stories, one of the most difficult situations that architects have to deal with is water penetration. And they love the idea about having a continuous piece of roofing material across our roof to lower any risk of water penetration. So very simple design. So now let's talk a little more about energy efficiency and some of the kind of key concepts that has become really core to more of our conversations today as we look at the future of climate change, of reducing carbon emissions, and ultimately trying to get towards net zero. And so one of the things that I want to try to challenge ourselves today to think about is that there are many paths to reducing our carbon emissions. There are many paths to net zero, and we may not believe it, but there are also many technologies available today that can help us get there with a little bit more education, a little more deployment, and acceptability of some of these technologies. So I want to talk about a few use case scenarios of where HCHB was used to improve both the indoor environment, the indoor air quality, and ultimately reducing the energy usage and the total carbon emissions of some various distribution centers and fulfillment centers. So this is actually a retrofit case study of a large 500,000 square foot warehouse located in Cleveland, Ohio, that was actually fairly similar to probably many existing warehouses out there today. And those existing buildings utilize indirect fired recirculation unit heaters. So this building had, again, about 500,000 square feet, was located in Cleveland, Ohio, had 61 operable dock doors, and that tenant had very uneven temperatures, very cold dock doors, very poor indoor air quality, such that there was no mechanical ventilation in this space. So this space was primarily ventilated through natural infiltration and operable dock doors. And what the HCHB system allowed the end user and the occupants to see was much more even temperatures, better indoor air quality by providing ventilation and providing mechanical ventilation where there was none, and saw a massive amount of energy reduction. In this space, they saw their total energy usage dropped by about 31%. Based on the site-specific typical utility rates, they saved about $60,000 a year in annual energy costs. Again, from a carbon emissions perspective, they actually reduced about 317 metric tons of CO2 equivalent emissions by reducing the energy usage and reducing the gas usage and reducing the electrical bill usage. They were able to greatly reduce the CO2 levels, emission levels in that building. And ultimately, again, from the key theme for us to learn today, the HCHB system added mechanical ventilation, improved the indoor environment, and lowered their energy yield, their energy bills, and ultimately the emissions in that building. Secondly, here's another retrofit case of a larger, I would say, industrial distribution center This happens to be a large distribution campus that was located in Illinois. It was about 8 buildings altogether that totaled about 1 million square feet. This building had actually a distributed hot water boiler and unit heater systems. So this distributed boiler system provided the heat to all of the outlying buildings, and they had, again, no ventilation. They had no forced mechanical ventilation. They had very drafty, cold, uneven temperatures. They had high maintenance costs, high gas costs, and high electrical bills for distributing and sending out that hot water heat to all the outlying buildings. And what they saw was they actually retrofitted the entire building with a decentralized HVAC space heater system with more even temperatures, forced mechanical ventilation, and by utilizing the zones and high velocity, they were able to get much more even temperatures, such that they saw a massive reduction in gas and electrical bills. What this facility saw was about a 42% total energy savings reduction. These dollars are quite substantial. Granted, this is a pretty large facility, about 1 million square feet. However, they saw about $312,000 of annual energy cost reduction. And from an emissions perspective, they had almost 2,000 metric tons of CO2 equivalent emission reduction by utilizing the decentralized HCHB system. So again, key theme, added ventilation, improved the indoor air quality, and massive reduction in energy and emissions. And finally, I'm going to show really a kind of side-by-side new construction story of really kind of the real-world example of our thermodynamic lesson we had earlier today, which is the thermodynamics and the theory is all nice, but what happens in the real world? Well, this is actually 2 large fulfillment centers. One was located in Kansas that utilized an HCHB high temperature heat and ventilation system, and another building located in Columbus, Ohio that utilized the low temperized draw-through makeup air system. Both systems had the same building construction, the same types of usage, the same square footage, the same numbers of units. They both utilized quote-unquote high-efficiency direct-fired combustion. However, the core principles of HCHB with more usable BTUs and more energy transfer per CFM, what they saw was that the HCHB system had 42% total energy savings reduction. So really, this is the proof in the pudding for our thermodynamic lesson. By removing the blower, by increasing the discharge temperature, by deploying HCHB technology compared to low temperized makeup air, massive energy savings and massive emissions reductions. Over 1,000 metric tons of CO2 emissions were reduced in the facility that deployed the HCHB systems over the low temperized draw-through systems. So again, we have a long path to get to our CO2 emissions targets over the next 10, 20, 30 years. I think the thing I'd like to challenge you all is understand there are multiple paths to reducing emissions. There are widely deployed high-efficiency combustion technologies available today to get us to where we can get to lowering emissions and net zero. I mean, one thing that I would like to challenge ourselves as an industry as we think about these large warehouses and these large distributions and these semi-heated spaces, you know, this building type, this construction is ripe for net zeros. Unfortunately, many of our tenants and users that look at fulfillment centers and warehouses as a necessary evil of low cost and get me square footage as fast and as quickly as possible. However, I think as an industry, we can challenge ourselves to improve our standards. I think these buildings, because of their low energy impact, because of their low BTUs or kW per square footage, and because of their large, wide open roofs, we can have a very simple path to net zero. We can utilize HCHB to have a very low kWh usage, a very low BTU usage, and by utilizing a right-sized PV panel, we can get to net zero much quicker. I think as a design community, we have a lot of challenges ahead of ourselves to get to net zero in the next 20 or 30 years. However, I believe that we can get there in this building construction, in this building type, by utilizing technology we have today and increasing the design standards and the expectations of our clients. So with that, that concludes the technical proportion of our presentation today. And it looks like we have some questions that have come through our chat here today. Thank you for those that have put those questions into the chat. If you have not, please feel free to put those questions in. We have some time to go through those questions, so please submit those now. I'll do my best to answer as many as we can. And if I don't get to your question, no worries. We will try to connect with you after the presentation. But let's go to some questions. All right, one question from Victoria. She asks, do you see that most facilities install HCHB units also utilize heated air curtains at overhead doors? Yeah, great question. You know, heated air curtains, you know, are a great way to really reduce and minimize that infiltration. And really, those air curtains are really what we're trying to do, is to lower the infiltration rate. And, you know, I think one key concept of HCHB that the mechanical ventilation proportion offsets natural infiltration. So ultimately, if we think back to maybe some of those use case stories, those buildings that didn't have any mechanical ventilation were very negative, had very poor, very high infiltration and very poor temperature control along the perimeters. So air curtains are phenomenal in those situations. What I see, I would say many facilities that utilize HCHB, they are primarily not using heated air curtains. I would say at least where the operable dock doors and overhead doors are, operable dock doors. Now, I have seen some manufacturing facilities that have heavily trafficked overhead doors. So I think about the typical dock door, which is your standard 9x10, maybe door seal type a dock door where you have a box truck backed up and an air curtain, has fairly low infiltration, but those big roll-ups, those 14x16 overhead doors, those can have a massive infiltration, even in a relatively neutral pressurization system. And I would say in those instances, and primarily when we maybe are operating outside of a traditional warehouse and more into a maybe heavy manufacturing where those overhead doors are used quite extensively, maybe we've got a manufacturing facility that is bringing in product, bringing in raw steel, bringing in inventory that may be stored outside and bringing those in and out through fork trucks all day long. That's where I see heated air curtains becoming pretty impactful and pretty helpful if you know that there's going to be a large overhead door that's going to be open for large extents of time. A lot of the standard dock doors that have seals, I think, are the HCHB system can really help offset that natural infiltration quite well, such that air curtains aren't needed. Yeah, next question from Jason. Are buildings using HCHB at a positive pressure? Are there any precautions necessary to address building leakage? Yeah, that's a great question, Jason, and definitely something to keep in mind as a design engineer. Really, when we look at HCHB, a right-sized HCHB system, because we have so much heat in a small box, because we have so much net BTUs in a small volume, typically HCHB systems can cover all of the conductive loads and all of the heat loss without overpressurizing. You know, depending on your building construction, and even today in the newer construction, you know, with tilt-up construction and tighter building codes, you know, these buildings are getting pretty tight. However, I have not seen a perfectly tight building. I always like to use the old adage, if you pick up any large warehouse and drop it in the Atlantic Ocean, when any of our general contractors or architects feel confident that building would float? And obviously no, because we know that there's always going to be crash construction. There's always going to be natural infiltration. However, what I've seen is that right-sized HCHB can provide enough heat to offset that natural infiltration. Now, that doesn't mean that throughout the year there's going to be conditions where I might need to bring in more air than would naturally breathe. And so in that case, always recommend to have some element of adequate relief. Now, in most cases, that relief is going to be the natural cracks of construction, the natural infiltration paths, or those standard cracks of construction, the operable dock doors, or any of the air gaps we see around the doors or dock doors. And we're going to basically take those infiltration paths and make those exfiltration paths. However, I always recommend that design engineers make sure that they've looked at having adequate paths of relief that aren't primarily just the dock doors or just the crash construction. And so you may need to have some other elements of barometric relief dampers to create enough pressurization. However, again, we are not talking about very pressurized buildings. The ventilation requirements in these buildings are fairly low. The infiltration rates are fairly high and from a standard construction, and so we are more often not operating at a neutral pressure. Got a good question here. Nicholas Baxter, is there a minimum safe distance from the 160 discharge for occupants? Yeah, good question. From a safety standard, there is a zero clearance to combustibles for these technologies. Because of the safety standards require some making sure that it is safe to deploy these systems in many operable spaces. Really what comes down to is if you look at that 160-degree discharge, that discharge temperature is going to mix with that induction air extremely quickly, such that we see in most applications, again, put yourself in a large fulfillment center, a large distribution center, and I'm putting these systems typically on the roof or hanging up high in the ceiling. They're going to be anywhere from 20 to 30 feet off the floor, and I'm trying to use that high velocity to push that air and pull that warm, stagnant air from the ceiling down to the floor, such that really if you walked in front of one of these units, you would only feel maybe an 80 to 90 degree sort of air across at the floor. However, that want to make sure that we don't put these systems maybe right over a workstation, right over an office, or right over a desk inside the warehouse. Make sure that we put those units somewhere that allows us to get a good, clear path to the floor to allow for that induction and allow for that air mixture. But good question. A question from Ted. It says, all of your examples center around warehouse and distribution centers. Are there other building types that HCHB would be a good practical solution for? Yeah, great question, Ted. I think one of the things that we've seen over the years is, obviously these systems were originally designed and deployed in large warehouses and in large fulfillment centers. However, they are not the only building type that has ventilation needs. They are not the only building type that has large, high ceiling where stratification becomes an energy hog, and they're not the only buildings that have, I would say, typically heated and ventilated spaces. So we are seeing even more adoption of this technology into heavy manufacturing, into aircraft hangars. Aircraft hangars are fairly similar to a large warehouse. Big operable doors, big tall ceilings, typically not cooled. It's just a heated and ventilated space, and they can be a fantastic solution for ventilating spaces and lowering the energy uses of aircraft hangars. Even, I would say, soccer facilities, indoor practice facilities. We've seen some of those indoor sports facilities that, again, have very high ceilings, have the need for ventilation and heat, and oftentimes in these indoor practice facilities, they don't like ductwork. They don't like to put fans. And so the HCHB system is a fantastic solution for them to make sure that I'm ventilating the space and I'm getting air mixture throughout the building. So, yes, many other facilities outside of the typical warehouse and distribution center. As always, if you ever feel like you have a need, the best way I try to think of it is if you have a building or a space that is roughly greater than 10,000 square feet, a ceiling that's higher than 20,000 higher than 20 feet, and we need ventilation and heat. Fantastic application for HCHB. A question from Rob. We got a chance for one or two more questions, and then we'll have to connect with those folks after the call. But a question from Rob says, in a distribution center with many loading open docks, what's the best location for HCHB relative to the loading dock doors? Yeah, what we have seen is the best application and the best positioning for HCHBs is actually around the perimeter, typically over those loading dock doors. Typically in the loading areas, there's going to be some kind of a staging area, so more often than not, we have a clear path to the floor. And secondly, if you look at a large warehouse, really the perimeter and where those opera dock doors is my greatest need for heat and ventilation. Middle of the building, there's actually very little skin losses, there's very little infiltration because it's primarily around the perimeter. So what we see and what we recommend to engineers is try to actually put those units right above the dock doors, maybe one column in, such that we have a clear path and a clear way to get that heat and ventilation to the floor. And what it'll do is it'll get the heat where we need it and actually help almost pressurize those dock areas right there at the source. So as always, though, every building is going to be different, but that is where we see most of those facilities most of those systems being situated is actually near those dock doors. We'll get time for one last question, then I think we'll have to turn over and try to connect with some guys offline or in email. But we got a question from Nabil. It says, is cooling available? Yeah, great question, because it's one of the challenges with HCHB that we are trying to look at is how do we work and how do we interact with cooling systems? Now, what I'll say is that primarily a lot of these facilities are what I would say designated under ASHRAE as semi-heated spaces. They don't typically have cooling systems with them. They are primarily just heated and ventilated. However, there is a growing need for people to either add cooling or we're looking at even more cooling systems being deployed in large warehouse fulfillment centers. And what we have seen is that really when you start to try to combine your heating, your ventilation, and your cooling systems, you start to make trade-offs. You can't get the best of everything in one simple system. Oftentimes, with some of the, I would say, challenges and limitations of vapor compression, large cooling systems need a large volume of air, and they need, because they have typically low delta T's from entering to leaving. Unfortunately, I have not seen a low temperature cooling system yet. Maybe it's a room for any of our R&D professionals out there to find ways to deliver very cold temperatures and induce air mixture and try to get more cooling in a smaller volume. Haven't seen that yet, but would love to rise the challenge. But from a realistic application perspective, what we see is that many design engineers do what we call as a heat with heat and cool with cool. So they would actually use the HCHB systems to be the primary heating system because we can heat a large open space. We can heat a 1 million square foot facility with 8 to 10 devices and very little ducting and very little fan energy. However, from a cooling system, we need that additional volume of air, and we need much larger ducting systems to be able to get good mixture from a cooling perspective. However, there's a lot of energy savings by not asking your package rooftops to do all of the heating, because ultimately a gas pack in a standard 25-ton package rooftop is no better than a indirect fired unit heater. Actually is worse because it adds a lot more fan energy. So your package rooftops utilize a lot of energy to heat these spaces. And again, most of these large facilities have very little simultaneous heating and cooling loads, so they can utilize a massive amount of energy from a ducting perspective, fan energy perspective, and a heating perspective. So that's where we try to help our clients heat with heat and cool with cool. With that being said, that's all the time we have for questions. Again, thank you everyone for joining today. Really appreciate the great questions. Wish I had more time to go through any and all of them. We will try to connect after the presentation. And as always, if you have any, hopefully if you have some projects or if you have some ideas or you love to just talk about how HCHB might be better deployed, we'd love to connect. But that is all we have for today. That concludes our presentation, and thank you all for being here.